Hey, what's up, guys? So in this video that I'm gonna to prove a simple results called the triangle counting lemma. Okay, so this lemma, if you start with this TCL lemma plus the Zamaradi regularity lemma that I just proved in the previous video, that you can prove very weird results called the triangle removal lemma. And this lemma can be used to solve a lot of interesting combinatorics problems. Okay, so I will prove triangle removal lemma in the next video, but let's prove triangle counting lemma. So let G be a graph on vertices and the X and Y be subset of vertices, and which are pairwise epsilon regular. Then the edge density is large enough. Then one can see, and the number of triples that in X and Y and Z forms a triangle is at least this number. Okay, so this is X, this is Y, this is Z. So this just tell you that the number of triple, it is X, it is Y, it is Z that forms a triangle. The number of triangle is at least this number. Okay. Sorry. Okay, so proof. So the idea is basically using the epsilon regularity. So we first notice the following. So I can define a set omega which X belongs to X, and X has less than dxy minus epsilon omega, y neighbor. So this set all the set which X has less than this number of neighboring Y. Okay. So this means that this is X, this is Y, this is Z. So I ask what's how many number of X here has less or equal to, let's say maybe, yeah, less or equal to dxy minus epsilon y nodes. Okay, so claim is very simple. Omega is at least cannot greater than epsilon x. Okay, so this is by regularity. Okay, the reason is following, right? So we can consider let's say omega is a subset of x, and let's say y just take y. Okay, so we calculate the d omega y. So by definition, right? So if not, right? If not means that omega is greater than epsilon x. That means that d omega will be okay. So you claim I claim this guy, right? So if omega right, then that means that if omega is greater than epsilon x, then we satisfy then this omega satisfy the regularity condition, but d omega y will be less than 6 dxy, right, minus epsilon y for each number nodes in omega times omega, right? So this is h divided by the density. So this is dxy minus epsilon, and this violate the regularity. Okay, so remember regularity tell you that d omega y minus dxy is less than epsilon. Okay, so you must have d omega y less than dxy minus epsilon. Greater than dxy minus epsilon, or less than dxy plus epsilon, and then we know that dxy is at least greater than 2 epsilon. Okay, so this means that we must have this. Okay, so now we can we have this picture. So we have x and y and z, and then we know that less than epsilon x, less than epsilon less fraction x has a lot of neighbor, right? So it has a lot of neighbor. So let's say I pick for each x belongs to the rest. Let's say I pick x here. So there will be some lots of nodes which connected to x, right? There's some nodes here, and they're all connected to this x. And the number of these nodes is at least greater or equal to dxy minus, sorry, I use this y to indicate this y. Okay, so times y. Okay, so the same reason, right? Less than epsilon x is connected to z. Okay, so we can safely say that there are less than 2 epsilon x. These x are connected to the same for the same reason connected to z. Okay, so we have a lot of here. Okay, so these are greater or equal to d y z minus epsilon z. Sorry, this is x. Okay. So now we are happy, right? So given x, we can given x here, then we can find this here and then some nodes here. Okay. Now finally, by regularity, right? So by regularity, I can consider these nodes as subset y prime. This is subset z prime. Okay, so by regularity of yz, then I know that the number of edges, right? So the number of edges, which is called e y prime z prime, is d of y prime z prime times y prime z prime. Okay, and the d of y prime z prime is at least greater or equal to d y z minus epsilon, and y prime r z prime, and by definition, is basically at least d of x y minus epsilon y, and d of x z minus epsilon z. Okay, so these are the number the number connected to this, right? Connected to y and z. Okay, so this forms a triangle, right? So for each x, you can always find a pair such that this forms a triangle. So the number of triangle is greater or equal to this guy times 1 minus 2 epsilon x. Okay, because for each x, then there is always a y and z, and for this two part, then we use regularity lemma proof. Okay, so this is the triangle Conti lemma. Okay, so next video that we will use this lemma and plus the Zamaradi regularity lemma, then I will prove this famous triangle removal lemma. And this also can be used in theoretical computer science. There is an idea called proper testing. Especially there's a called graph proper testing, which is interesting open area. See you guys next videos.